Hi everyone, this is Dr. Saida Falafini from Cal Poly Pomona. In this video, we are going to look at two examples related to MMS type of queuing system. In the first example, we are looking at a bank with two servers. The average time it takes to serve a customer is 1.2 minutes. And on average, 80 customers per hour arrive to a bank. And the inter-arrival time and service times are exponentially distributed. So these are the information that we have, and then we want to answer a bunch of questions related to this bank. So first, let's see what we can learn from these first couple of bullets. So this part, the average time it takes to provide service to a customer. So obviously, if we think about if this is a service time or service rate, this sentence is giving us the service time. So then we have to calculate the service rate. So if service time is 1.2 minutes, then service rate, which is 1 over service time, is 1 over 1.2 customer per minute. And if we multiply that by 60 minutes per hour, that is going to be 50 customer per hour. Okay, so that's the service rate. Then this bullet is telling us that on average 80 customers per hour arrive to the bank. Again, think about it. Is this arrival rate or inter-arrival time? So the information given here is arrival rate, lambda equals to 80 customer per hour. We also have two servers in this bank, so that tells us that this is M2 type of system. We also learn here that the inter-arrival time and the service times are exponentially distributed, so that's why I put to capture the fact that the inter-arrival time and service times have exponential distribution. So the type of system that we have is MM2, which falls under the category of MMS that we learned in previous sessions. So we are going to use those formulas to answer the questions. Before we answer any one of the questions, let's first calculate rho, the traffic intensity, which in this scenario is lambda over S mu, and see if rho is greater than or equal to 0 and less than 1. And if this queuing system is stable, then we can go ahead and answer the questions. So lambda is 80, S is 2, and mu is 50. So rho is going to be 0.8, which is greater than 1. And that's a good thing because that shows this queuing system will reach a steady state. So we can calculate the values and answer the questions. So for part A, it asks, what is expected number of customers in the bank? So average number of customers in the bank, that's L. In this system, we can calculate L as LQ plus LS. Average number of customers in the queue plus average number of customers in the server shows average number, will form average number of customers in the system. LQ equals to probability of J greater than or equal to S. S in this system equals to 2. So that's probability of J greater than or equal to 2 rho over 1 minus rho, and LS equals to lambda over mu. So to be able to this answer, I have to find this part first. And this is the part that I can find from table 6 of the textbook. To be able to find probability of J greater than or equal to 2, I need to know rho, which is 0.8, and I need to know S, which is 2. Then using table 6, probability of J greater than or equal to 2 is going to be 0.71. Then I can calculate L. L equals to probability of J greater than or equal to 2, which is 0.71 multiplied by rho, 1 minus rho, plus 80 over 50. And that's going to be 4.44 customers. So this is the average number of customers that are in this bank at every point of time. Part B wants to know what is expected length of time a customer spends in the system. So the length of time, so the time that a customer spends in the system. The length of time that a customer spends in the system, that's going to be W. And to be able to calculate W, we can say equals to L over lambda, Little's formula. And L we just calculated is 4.44. Lambda is 80. This is going to be 0.055 hour or 3.3 minutes. In part C, we need to know fraction of time both servers are idle. Fraction of time that both servers are idle is basically when there is no customer in the system, because if there is one customer in the system, one of the servers will be busy. So if we want both servers to be idle, no one should be in the system. So the fraction of time that no one is in the system is going to be shown by pi 0. And the formula for pi 0, as we show in previous session, is s factorial, probability of j greater than or equal to 2, 1 minus rho, s rho to the power of 2. So s here is 2 factorial. Probability of j greater than or equal to 2 that we got from table 6 is 0.71. 1 minus rho, 2 multiplied by 0.8 to the power 2. And this value is going to be 0.11. So 11% of the time, both servers are idle. That means no one is in the system. Now let's go to part D. In part D, we want to know what fraction of the time a particular teller is idle. Okay, so part D. Remember, we have two tellers in the system. What we calculated in part C is that the fraction of time that both these tellers are idle. However, in part D, we want to calculate fraction of time a particular teller is idle. For example, the first teller. What fraction of time the first teller is idle? We want to calculate that. So the first teller will be idle under two scenarios. When there's no one in the system, that would be pi 0. Obviously, when there's no one in the system, the first teller will be idle as well. The second scenario is that when there is one person in the system, one person is coming to the system, but this one person goes to the other teller and gets service in the other teller. In that scenario, this teller is idle as well. So when there is one person in the system, that's pi 1. So that's the fraction of time that there is one person in the system. However, with 50% chance, this person goes to this other teller and gets the service in this other teller. And that happens with a chance of 50%. So when any one of these scenarios happen, then this particular teller is idle. So when the scenario 1 happens, when there is no one in the system, or plus there's one person in the system, but with the probability of 50%, this other person goes to the other teller. So if I can calculate this value, then I can calculate percentage of the time that a particular teller is idle. Here we know the value of pi 0 from previous part C. So now I have to calculate pi 1. And pi 1, the formula for pi 1, if you remember from previous session, since here pi j or pi 1 is for a j which is less than s, because the j here is 1 and s is 2. So if j is less than s, the formula that we calculate for pi j was the first formula that we showed in previous session. That's going to be s rho j pi 0 over j factorial. S here is 2 rho 0.8 to the power of j, which is 1, pi 0.11 over j factorial, which is 1 factorial. This is going to be 0.176. The answer to part D, which is pi 0 plus half of pi 1, is going to be 0.11 plus half of 0.176 that we just calculated, and that's going to be 0.198. So about 20% of the time, a particular server, for example, this one, is idle. Now let's look at the second example. In the second example, we want to see how many tellers we need to hire in a bank to minimize the cost. Okay, so that's the question that we have in front of us. On average, it takes 2 minutes to complete a customer transaction. So what does this information is giving us? It takes 2 minutes to complete a customer transaction. So you have to be able to just read this sentence and figure out what is given to you here. Is it related to arrival time or service time? If, for example, here the information is related to the service operation. Is it service rate or service time? This is service rate. This is service time here. So, okay, it takes 2 minutes to complete a customer transaction. So service time is 2 minutes. Service rate mu equals to 1/2 customer per minute. Here, I'm not going to transfer this to customers per hour, and you will see in a second why. So I'm just going to leave it as is. On average, 2 customers per minute arrive to the bank. So that's arrival rate, lambda. That's 2 customer per minute that arrive to the bank. It takes $9 per hour to hire a teller, and every minute delay of customers in line will cost the bank 5 cents. So it's important to pay attention to this one. So it says that waiting of the customers in line. So in the queue, the waiting of the customers in the queue will cost the bank. Sometimes in some service, in some problems, it may tell you that the waiting of the customers in the system may cost you some money. So pay attention to this one. Here we know that the waiting of the customers in the line will cost the company. Okay. So now the question is that given all these factors, given the fact that we know that if we hire more teller, we have to pay them some money. At the same time, if you don't hire enough teller, the customers have to wait longer in the line, and that will impose cost to the bank in a different way. So the question is that what is the right number of tellers? What is the optimum number of tellers that we have to hire in this bank to minimize the cost? Okay, so we want to minimize the cost. If you consider the cost component in this bank, that's going to be the cost of tellers plus cost of waiting in the line. If I want to answer this question about what is the optimum number of tellers in the bank, I have to calculate this cost for all possible values for number of tellers in the bank and then pick the number of tellers that minimizes this cost value. Okay, so let's see first of all what is if I want to look at possible scenario for the number of tellers in the bank, which one of those scenarios are possible and which one of them are not possible at all. So to be able to do that, first let's look at rho, the traffic intensity. Rho equals to lambda over S mu. Okay, lambda here is 2, and S, we don't have that value. Obviously, that's the one that we want to find out. And then mu is 1/2 or 0.5. Then we know that the rule or the condition that we want to hold for rho is that rho should be less than 1. So if I want this expression to be less than 1, that means S should be greater than 4 or S should be greater than or equal to 5. Okay, so the number of servers in the system should be at least equal to 5 for this system to be present in the steady state and for the system not to explode. So when I talk about possible scenarios, is that the number of servers that are the possible number of servers that we are going to look at are 5 servers, 6 servers, 7 servers, and so forth. So we are not going to look at possibility of having 2 servers or 3 servers and so forth, because in those scenarios, the system will not be in the steady state, the system will explode. So we are not going to look at this queuing system in those scenarios. So the number of servers in the system should be at least 5 or greater than 5. So we are going to look at these scenarios. So the first scenario is when the number of servers in the system is 5. So then I want to look at the cost, and I want to look at the cost. So when we look at the cost, we have to look at the cost per unit of time. So I want to look at the cost per minute. So that's going to be the cost of tellers per minute plus the cost of waiting in line per minute. So for the cost of the tellers per minute, we know that we have 5 tellers. So in this scenario, we have 5 tellers. So there are 5 of them. And we know that for each one of the tellers, we pay $9 per hour. So this is $9 per hour. However, I want here the unit of time to be the minute. So if I pay $9 per hour, that's going to be $9 per 60 minutes. So this is going to be the amount of money that we pay for each minute. So this is going to be amount of dollar that we pay in each minute. Then I have to calculate the cost of waiting in the line. That's going to be the number of people that are waiting in the line at any moment of time, multiplied by the cost of the waiting in line per minute. Okay, so we have to add that cost component here as well. First of all, this 9 divided by $60 per minute basically is equivalent to 15 cents per minute. And then I'm going to calculate LQ and then multiply it by the cost of waiting in line per minute. So LQ equals to probability of J greater than or equal to S rho over 1 minus rho. Here S equals to 5. So that's probability of J greater than or equal to 5 multiplied by rho over 1 minus rho. So to be able to calculate probability of J greater than or equal to 5 from the table, I need two things. I need to know S, which is 5 here, the number of servers. I also need to know rho. Rho equals to lambda over S mu. Lambda equals to 2. S equals to 5 and mu equals to 0.5. And this is going to be 4 over 5 and 0.8. Okay. Now that I know the value of S and the value of rho, then from table 6 from the textbook, the probability of J greater than or equal to 5 is going to be 0.55. Then I can go back to calculating LQ. So LQ is going to be 0.55 multiplied by 0.8, which is value of rho that we just calculated here, divided by 1 minus 0.8. So the value of LQ is going to be 2.2 customers. So on average, about 2 customers are waiting in the queue. So then the total cost per minute is going to be the cost of the server per minute. This is going to be 5 multiplied by 15 cents per minute plus number of people that are waiting in the queue, LQ, which is 2.2, multiply the cost of the waiting in the queue per minute. And here we have that for every minute delay of the customers in the line or in the queue, the bank pays 5 cents. So for every minute of waiting in the line or in the queue, we pay 5 cents per minute. So the cost per minute in this scenario is going to be 86 cents per minute. Now we are going to repeat everything for the other scenarios. So this is the cost associated with S equals to 5 or 5 tellers or 5 servers in the system. Now we are going to look at S equal to 6 when we have 6 tellers in the system. Again, I need to look at the cost per minute, and that's going to be the cost of server per minute and the cost of waiting in line per minute. So the cost of server per minute, so since we have 6 servers, it's going to be 6 multiplied by 15 cents per minute plus the cost of the waiting in line. And here we can just see that the cost of servers on its own is going to be 90 cents per minute. Okay, and we still have to add the cost of waiting in line, which we haven't done yet. So just the cost of server on its own is greater than the total cost in previous scenarios. So I don't need even to continue with calculating LQ and calculating the cost of waiting in line for this system, because for sure the total cost in the system will be greater than 90, which is already greater than the cost associated with 5 servers in the system that I already have calculated. So I don't need to continue with calculating the cost, and I can conclude that the optimum number of servers in the system that is going to minimum the cost of servers and the cost of waiting in the line is 5 servers or 5 tellers, and the cost per minute will be 86 cents.